Good morning, friends. So, today we are going to start our second chapter of reinforced cement concrete. As discussed in the first chapter, we had learned about the concrete technology, various types of cement, different characteristics and properties of aggregates, fine aggregates, coarse aggregates, and water. And in this chapter, we are going to learn the basics of mixed design. Today we are going to learn various topics which includes the introduction of mixed design, methods of proportionating of concrete mixes, grades of concrete, compressive strength of concrete in structures, and mixing, compacting, and curing of concrete. So guys, let's start with our introduction. First, let me define. It is defined as the process of selecting suitable ingredients of concrete and determining their relative proportions to produce concrete of certain minimum strength and durability. Strength of concrete varies as an inverse of water cement ratio. After mixing and proportionating, these resulting concrete should have following properties, like it should possess maximum density so that it will be strongest and watertight. Fresh concrete should have enough workability so that it can be placed in formwork easily and economically. The cost of materials and labor required to form concrete should be minimum. The second part is the methods of proportionating of concrete mixes. There are various methods as listed below. We will discuss each method point wise sequencing. Okay, so let's start with the first method. It's arbitrary method. In this method, it is used only for work of small magnitude and of moderate importance. The fine aggregates should fill the voids of coarse aggregates to give a dense concrete. The ratio of cement, sand, and coarse aggregates should be generally 1:n or 2n, depending upon the strength required. The amount of water required is decided on basis of workability, which in turn depends upon the type of work and compaction. There are different grades of concrete like M5 and 7.5. Like we say that the proportions of M5 according to arbitrary method is 1 is to 5 is to 10, while of M15 is 1 is to 2 is to 4. M10 is 1 is to 3 is to 6, and M25 is 1 is to 1 is to 2. There are different various types of proportioning depending upon the grade of concrete. So let's move on to the second method, that is minimum voids method. It is also called as unsatisfactory result obtained method. In this method, the quantity of sand used should be such that it can be completely filled with voids of coarse aggregates, and quantity of the cement should be such that it completely fills the void of sand to obtain a dense concrete with minimum voids. But in actual practice, the quantity of sand used is kept 10% more than the voids in coarse aggregate, and the quantity of cement used is kept 15% more than the voids in sand. The third method is maximum density method. It is much unpopular method. Many of that has not even listened about that method. Okay, so it has the minimum void method was improved to get grading of materials to get maximum density by flow. It has not much information. The formula is given by P is equal to 100 maximum size of aggregate upon percentage by weight of material finer than diameter, the uh, the whole power 1 is to 2. And the last method is fineness modulus and water cement ratio method. It is given by the proportion of fine aggregates to coarse aggregate plus fine aggregate. The grading of aggregates should be such that in fully compacted state, the total surface area of aggregates and voids in the mixture are at least. Some of the properties are lower water cement ratio within certain limits results in increased strength. Higher water cement ratio increases the workability but reduces the strength. Optimum water cement ratio for required strength of concrete should be decided from graphs and expressions. Amount of water Amount of water less than the optimum reduces the strength 10%, less water optimum. An increase in 10% water above optimum results in decrease of strength by 15% approximately, while an increase in 50% may decrease the strength to one half. There's various practical values of water cement ratio for structural reinforced cement concrete. Some of them are 1 is to 2 is to 1 is to 2 is to 4 concrete for 0.5, 1 is to 1 is to 2 concrete for 0.45, and many more. The vibrated concrete requires less water cement ratio, hence more strength. So the quantity of water can be decided according to the following thumb rule. If the weight of water is equal to 4% of weight of total aggregate plus 28% of weight of cement, while on the other hand, weight of water is equal to 30% of weight of cement and 5% of weight of aggregate. So moving forward to the grades of concrete. There are various characteristics. There are different aspects to measure the grades of concrete. First is the characteristic strength, second is increase in strength with age, tensile strength of concrete, shrinkage, elastic deformation, creep of concrete, and so on, and we will discuss it one by one. The first is characteristic strength or grades of concrete. Characteristic strength can be defined as the strength in Newton per mm square of material below which not more than 5% of the test results are expected to fall. So here's the table given. There are three groups: ordinary concrete, standard concrete, and high strength concrete, with each grade M10, M15, M20 as ordinary concrete, M25 to M55 as standard concrete, and M60 to M80 as high strength concrete, which is used in different areas of work. If you want to construct a residential building, then you can use ordinary concrete, but if you want to construct a bridge or something else like a skyscraper, then you have to use standard concrete. But if you have to construct a dam like structure, then you have to use high strength concrete. So these are the third table shows the specified characteristic strength of 15 millimeter cube at 28 days in compression, Newton per mm square. All the values are in given dimension, the given units. That's 10 to 80 Newton per millimeter square. According to IS 456, the IS code of concrete technology recommends that minimum grade of concrete shall not be less than M20 grade for R.C.C work. So let's begin to the next. The second is increase in strength with age. The increase in strength with time depends upon grade and type of cement, curing, and environmental conditions, etc. Design should be based on 28 days characteristic strength. Like in 7 days, the relative strength is 0.7 FCK. FCK is the symbol for characteristic strength. For 28 days, it's 1, and 6 months is 1.2 relative strength. Let's move forward to the tensile strength of concrete. The tensile strength of concrete is the flexural and split tensile strength, and it can be obtained as per IS 516 and IS 5816 respectively. The FCR, which is known as the flexural strength, has given by the formula 0.7 under root FCK, which is the characteristic strength in Newton per mm square according to IS 456. As per American Code of Practice, FCR is equal to 0.5 under root FCK Newton per mm square. Direct tensile strength is obtained by spilling test, generally by the formula FCT approximately equal to 0.6 FCR. Let's move forward to the elastic deformation. Elastic deformation is influenced by elastic properties of material, aggregates, and to a lesser extent by age of concrete, condition of curing, the mixed proportions, and type of cement. Let's take an example that static modulus of elasticity in Newton per mm square is equal to 5700 under root characteristic strength of cube in 28 days in Newton per mm square. That might be the elastic deformation. So moving forward to the shrinkage, the total shrinkage depends upon the constituents of concrete, size of member, and environmental conditions. In absence of text data, the total shrinkage strain for design may be taken as 0.003. Sorry, 0.0003. Sorry for that. And the last but not the least is the creep of concrete. In addition to the factors influencing shrinkage, creep also depends on the stress, age, and duration of loading. Like in 7 days, the creep coefficient might be 2.2, in 28 it's 1.6, and in 365 days, 1 year, it is 1.1 creep coefficient. So let's move forward to our different topic. It's compressive strength of concrete in structure. Please don't mind, the spelling is wrong over there. Sorry. Compressive strength of concrete in structure. Our next topic. Strength is found to be the decreased with increase in size of specimen because there is greater probability of presence of weaker element in large volume of concrete. Practically, strength does not decrease when size of specimen is increased beyond 450 mm. Strength of 450 mm cube might be equal to 0.85 times strength of 150 mm cube. Let's take the compressive strength of the structure as f dash ck. So the value may be f dash ck is equal to 0.67 times fck. The end friction restrains any specimen from failure. In cubes, it acts on whole length, whereas in case of cylinders, end friction works only up to 0.85 A, where 2 is the length of specimen. Therefore, cylinder compressive strength is actual and lower. So moving forward to the stress strain curve for concrete. The peak stress is at strain of about 0.002. The high strength concrete crushes at lower strain as its descending part is steeper, so it is more brittle. Crushing strain lies between 0.004 to 0.006. Ascending part is generally parabolic for all types of concrete. Curve is approximately linear for 0.6 times peak stresses. Here we have seen the different properties of this curve, which shows the stress in y-axis and strain in x-axis, with a differentiation of high strength concrete and low strength concrete curve. Moving forward, here we have seen the strain in ultimate strength. Maximum stress attained prior to failure is ultimate stress. For concrete, it is corresponding to strain of 0.002 for actually loaded member. Concrete strain at flexural strength is 0.3 to 0.4%. For design purpose, it is 0.35% generally. Moving forward to design stress strain curve for concrete. Ignore the curve beyond 0.35% strain. The partial safety factor, assume it as gamma m. So the design strength is FCK upon gamma m, where partial safety factor is 1 if only loads are considered, 1.5 for limit state of collapse, 1 for serviceability limit state, and more than 1 for ultimate values. So here is the stress strain curve for concrete. As we have discussed the different values of partial safety factor above, here you can relate it with them. Moving forward to the reinforced concrete. The flexural strength concrete is 150% of its compressive strength approximately. Therefore, concrete is strong in compression but weak in tension. Hence, tension flange is reinforced by embedding steel and concrete is allowed to crack. The beam should be under reinforced to ensure ductile failure due to yielding of tension steel rather than brittle failure of concrete. Brittle failure is sudden and hence not desirable. So, the reinforced steel has the carbon content in mild steel of around 0.25%. The alloying bars with carbon, nickel, and etc. increases strength is done by the hot rolling. Bars can also be strengthened by cold working. Grades of bars are given below, like for mild steel Fe250, it is 250 Newton per mm square. For high yield strength deform bars, it's Fe415 and Fe500 with 415 Newton per mm square and 500 Newton per mm square respectively. The F20 is a plain mild steel of M5 bars, while as discussed above, Fe415 and Fe500 are HYSD bars, where the modulus of elasticity is 2 into 10 to the power 5 Newton per mm square, whereas the yield stress is the 0.2% proof stress corresponding to 0.2% strain on unloading. Process of heat rolling reduces ductility. Moving forward to the actual and design stress strain curve of steel. You can see the difference between them. In the y-axis, it's shown the stresses in 250, 415, and 500 grade steel, while in x-axis it's shown the strain percentage for hot rolled and cold worked, for mild steel and HYST steel, high strength concrete and low strength concrete. The Fy is the characteristic yield stress, and the gamma m is the partial safety factor, where the partial safety factor is equal to 1 and 1.15 for serviceability limit state and limit state of collapse respectively. The strain in tension steel at ultimate strength is 0.4 to 1%. Therefore, in the range increases, is strength is insignificant, so it can be ignored. We do not designate reinforced bars with their ultimate strength as it is never reached in actual. Therefore, they are designated by their characteristic yield strength. Moving forward to the next topic, it is mixing, compacting, and curing of concrete. So let's study about the procedure. The first is the mixing. First, we have to mix the sand and cement in appropriate proportions in dry state. Then add coarse aggregate and with the help of shovel, mix the whole mixture thoroughly. Then add water. Above procedure is called as hand mixing. In machine mixing, coarse aggregates are filled first, allowed by the sand and then cement lastly. Water is added in revolving state when mixture is thoroughly mixed. For small scale work, batch mixture is used, while for large scale work, continuous mixture is used. The second procedure is transporting. There should not be segregation of aggregates. While transporting, water should not be added during the passage from mixer to transporting. The third procedure is placing of concrete. It should be placed before initial setting time and compacted. The formwork or surface receiving fresh concrete shall be properly cleaned, prepared, and well watered. At the time, large quantities should not be deposited. For vertical laying, concrete should be dropped from a reasonable height, otherwise segregation or bleeding may take place. Concrete should be placed in horizontal layers of about 15 cm height. The layers may be of 40 to 50 cm from mass concrete. Latence is the accumulation of excess water in upper layer. The fourth procedure is the compaction. Concrete should be thoroughly compacted during placing. With the use of vibrator, it can be compacted manually by rodding, tamping, or hammering for thin vertical member rodding. So the last but not the least, it's the curing of concrete. Curing is a very important part to make the concrete cool to release the heat of hydration. After placing of concrete, its surface should be kept wet for a certain period. It controls the temperature and moisture in concrete. Curing increases the strength of concrete gradually. Durability is also increased while permeability and shrinkage is reduced. Resistance of abrasion is also increased. Period of curing for ordinary Portland cement is about 7 to 14 days. Actually, period of curing depends upon the type of cement and nature of work. So our last topic is factors affecting methods of curing. The temperature should be kept minimum for dissipation of heat of hydration, and water loss should be minimum. Ponding with water up to depth of 50 mm. Covering concrete with wet jute bags and wet sand, raw dust, or the waterproof polythene sheets. Intent spraying with water and continuous sprinkling. Applying curing compounds like arylates, bitumen, sodium silicates, wax, linseed oils, chlorinated rubbers, etc. So guys, here is the end of chapter 2, the basics of mixed design. If you like my lecture, please share it to your friends and subscribe my channel if you are new to my channel. Like the button